Hmm?
Is that new chalk?
No, that's some of the older one. I think that's for kids. This is like very giant. Yeah. Some funky color. I'm not sure I want writing a pink. Let's see. No, not too bad. Mm-hmm.
Try it for once.
Okay.
Be nice.
Have you talked to Matt about that?
Yeah, I'll
Okay. Okay, sure. Okay, let's get started so we can finish a bit early. So what we're going to do, to be very efficient, talk about the second half of the class. What we're going to do is talk about persistence lens and several concepts about how can we statistically understand our polymer chain. Okay, so we started to talk about the different chains, about free joint chain as well as several other models, right? So when we talk about a free rotation chain as well hindered rotation chain, we now start to have more limitations to our polymer chain. Like bond angle, rotation angle, all these give restrictions to the polymer. It's getting more more realistic, but also gives some bad, complicate the mathematical process. So how can we think a process you can restore the simplicity of describe a chain using just a free joint chain mode? Longer segments. How does longer segments would allow you to get a free joint chain back? Like, Dane, yeah.
It's, I guess, just to approximate that entire section, even if it kind of moves around from the original direction, it ends up being that.
Yeah. Okay. It's a very, very nice answer. So what I'm trying to say is, what if we now use this picture? Consider if I cover the box, which are very hard to do because it's projector, but imagine my hand is covered over here. You only see this dot and this dot. And what happens is you actually would be able to describe this end-to-end distance using two models. Only consider the end-to-end distance, okay? So think about that. We have, let me see if this works out. Oh, not bad. The color looks okay. What if we have a second case where you actually would describe as a free joint chain model of m bonds, and each bond with bond length of b. You would have a case 2, end-to-end distance will be equals to mb squared if it's a free rotation chain, right? So like you see here, if we actually could make that happen, then you have now two models describe the same polymer chain. If I cover it up again, you don't see what's inside. We call it, they are statistically equivalent for two different models. Why? Because they behave similarly in terms of what's end-to-end distance, and they behave the same similarly in terms of contour length. In doing so, by converting a non-free joint chain model to a free joint chain model, we would simplify the math so much that we can calculate a lot of parameters very straightforward and easily. Okay? Conceptually, anybody has challenges understanding what's the difference between two models, how it'd be possible you can describe the same chain dimension with a different model? Anyone? If not, then let's move on.
I just have a question.
Yeah.
The big N is also number of bonds, or is it?
It's not necessarily equal to degree of polymerization. It's just a new set of the bond, N. Okay? Because in this case, the N will likely to be smaller, because B will get bigger, right? So imagine now you can describe this. Again, I want to use polyethylene as an example. If you have, let's say, 10,000 bond, each one is 1.5 angstrom internal length. If you consider polyethylene, C infinity is about, I won't say it's about number 5, okay? So you would have this will be equals to what's the final value of end-to-end distance square if you consider free rotation chain model. Okay? Yeah, this is characteristic ratio. This is the number of bond. We just give an assumption that it has 20 right? That's what you would get in the RE square. Now imagine if you can describe with different, with number of n can be just the degree of polymerization. I'm missing a 2. How could I make this mistake? Okay, everybody gets it? So now you get n. Think about this degree of polymerization. If you could equal to n 1000 multiplied by b squared would be equals to this particular value, then you could get statistically averaged segment length. Instead of consider bond, we now consider as a segment. In other words, if we do some quick math, this b would be equal to root of 10 multiplied by 1.5. And if somebody can help me get this, it should be about 5 angstrom. Maybe a little bit less than 5, okay? So if you multiply by this, I would just do a mass here. Let's say it's about 5 angstrom. So what this does is now tells you if you describe the same polyethylene chains for a molecular weight of 28,000 in a hindered rotation model, it's equivalent to if you consider a free joint chain model with less bonds, 1,000, and each bond is bigger in terms of size. Okay? I just gave an example. N need to be satisfy a secondary requirement is contour lengths need to be similar. Okay, so N may not be necessary exactly the same. Okay. Any questions so far for this particular part? If not, we can continue to talk about this slide. This slide talks about how can we get this effective chain length if we strip away all the angles and bonds. Okay. So in this particular slides, we're going to discuss what is called coon segment length. Coon segment length is basically effective bond length, as we just talked about right there. Coon segment length is statistically they were equivalent to a free joint chain that describe you non-free joint chain case. You need to have, for example, in this case, where we talk about the dark black one is what we originally talked about as free joint chain model or just a regular chain model where you have each bonds coming is a bond length as shown here. You have one attached to the other, then keep going. You would have end-to-end distance described as this R. And what the R value will be given that R squared will be C infinity N squared. C is the characteristic ratio we talk about. Because it's not a free joint chain for this particular case, for the black line, okay? So you have to have this C infinity there. Now, so conceptually, if we can delete the black line, only have the red line, but describe this with a free joint chain model, so each bond length will be larger, but they matches in the size, like I said there, end-to-end distance square will be NL effective square. Okay? Any questions so far? It's kind of a little bit quiet. Please ask me. Did I explain the motivation very clear why people want to ditch the free rotation chain model or hindered rotation model for free joint chain? Because later you will see it's much easier to discuss mathematically. And the reason you can simplify a non-free joint chain to a free joint chain is come up with equivalent model which has the same end-to-end distance and same contour length.
I guess
Lena.
I'm curious on the purpose of the coon segment.
The purpose of coon segment, why we describe it, it's called a coon segment. So this is just a way for you to simplify your models to be a free joint chain. So coon segment is basically the new bond length.
Is it representative of like one type of bond to another type of bond?
No, it's an ideal bond. It doesn't exist.
Okay.
It's basically a new three-dimensional model that the new bond length is now become this value. And NL squared is basically going to be the free joint chain model. This directly tell you what's the end-to-end distance. Okay?
So
Please?
Sticking with the assumption that the end end-to-end distance will be proportional to root n.
End-to-end distance will be proportional to root n. Yes.
Because this is just another. So this is just another way to represent what we've already been studying. We're not. None of the models we're looking at are any different. We're just representing it in a different way.
Right. That's correct.
Okay.
So you want, let's say, yeah, it's the same me, but the different way you describe me.
Yeah, it's just
So,
maybe you call this a pen and you call it something else in a different language. It's
Mhm.
effectively just that.
yeah, kind of. Well, it's really the final reason why people do this is they want to have statistical, easier way to describe our material. Okay.
We're still not looking at the real chain and whatever complications that come.
No. So that's called statistic segment. Statistic segment is basically a new term describe your real chain by free joint chain model. So let me repeat the important things again. So it's basically a free joint chain to describe real chain model where now in this equivalent free joint chain you don't need to worry about all the bond angle, etc. However, they still capture what is the physical dimension of the original real chain because they would satisfy the description that they still have the same end-to-end distance and they still have the same contour length. As I said, if I cover in a dark box, they would do exactly the same thing between two different models. Okay? No more question?
In terms of accuracy,
Please?
it's
Yeah.
almost relative to being the same thing.
Yeah, it's relative.
Accurate.
Yes.
One's not more accurate than the other.
No.
Okay.
It's basically the same. As I said, that in the real chain, because we know exactly what's the bond length, you know exactly the bond angle, you cannot just say my polyethylene will get a bond length which is 3-4 times using a free rotation chain model because that's not real, right? But now, in a parallel space, think about now we describe the same polymer chain just to use a free joint chain model with the bond length is bigger, which is called a statistical bond length, which is B or L effective in that case. Okay? Chain statistics. So we basically already kind of quite extensively discussed this. So for describe the same chain end-to-end distance, you can have characteristic ratio, bond length, bond number of bonds, and bond length, right? And you need to consider all the bond angle using this hindered rotation model in this particular case. However, equivalently, you can consider now if you have degree of polarization, now you can get a statistical segment length and use a free joint chain model to describe. And that would give you MB squared. If you look at the textbook, there is a table tell you what is statistically B value is, and you will see the B value will be much larger than original bond length. So if your bond length is here, if it's 1.5 angstrom for polyethylene, your statistic segment length will be about 5 angstrom, 3 times bigger. Okay? And if you search the textbook, it will have an extensive table. Yeah?
Can you define DP again, please?
DP is degree of polarization. DP is related to molecular weight divided by monomer molecular weight
Thank you.
or segment molecular weight.
Is it the same? Segment molecular weight, right?
Yeah. Okay. So this segment molecular weight is not necessarily depends on the molecular weight, because it's a term only depends on what are your rigidity of the polymer, or C infinity, as you can see. C infinity is a parameter will tell you what the B is, because degree of polymerization and number of bonds is fixed, or they has a linear relationship, right? So now, describing the same polyethylene chain, you now have two ways to think about that. Think about polyethylene chain we talked in the first class. You have two ways you can choose. First way is you need to know number of bonds. You need to know number of bond lengths, and you need to know what the bond angle and those rotation isomer state. That will give you basically end-to-end distance is real. Or you could be someone trying to take an easy route, or being smart is just I need to count degree of polymerization, which you can calculate, right? And you can easily get from molecular weight divided by segment and molecular weight. And if you know what its B value is, you can just apply a free joint chain, and B squared will give you the final value of the chain dimension. And they would behave almost the same. Does it make sense for everybody? And go to textbook. So, Sonia, which table is this? So if you go to table 6.1, it's listed all what's the B value and what is statistical value for the chain. Okay? And it's also listed C infinity, or characteristic ratio for common known polymer. I'm only going to scratch the surface about what is persistence length. So persistence length, by the name of definition, is basically talk about how the length along the chain for which the vector persists in the same direction. It's a very jargon language to say, but in other words, basically how long your chain would maintain its direction for how many segments. If you have persistence length is large, which means your polymer memorize where it's trying to go and being very persistent going around that direction. An example would be DNA molecular. And DNA molecular has a persistence length about 200 to 300 nanometer. So what that means, DNA is very rigid into the double helix form. It doesn't like to be bent or play around. Intermediate is conjugate polymer. It's a class of polymer that I study in my group, where it shows a lot of aromatic rings in the polymer backbone, because if you have fine membrane, you cannot just twist in the middle of it. Between the end of each one, you can have bond rotation, but around the bond, you don't have much rotation and ability to change. So even for conjugate polymer, we cannot say it's fully rigid, because it all depends on what the size you look at. It's similar scenario to a garden hose I want to talk about. Rigidity is all relevant. It's relevant to how big are you talking about. If you have a chain that's super long, it can bend as well. So that's what they're trying to do is a garden hose where locally, if you look at on the order of a few inches, it's relatively rigid. But if you put a size about several yards, it's actually bent back and forth. So what the physical meaning is, you have to compare the persistence length versus its contour length, or how long your molecule you are trying to compare. I'll give you three scenarios. If your persistence length, or how much long chain, remember direction, is much larger than its contour length, Is the polymer rigid or soft? Super rigid, right? If they're on a similar order of value, let's say your persistence lens is similarly in length as contour lens, then we actually call it semi-rigid. Or in a textbook you guys about to learn, it's called a worn-like chain because it's not super soft, but it's neither is rigid like a piece of rod. In the case that persistence lens is much smaller than your contour lens, then that's a flexible chain we have been talking about for a long time.
I'm sorry, can you say that last sentence one more time?
Yeah, so when your persistence lens is much smaller than the contour lens,
Okay.
we call our material is very flexible. And conceptually, you can think about persistence lens is like how far I remember where I want to go for the polymer chain. If it's just take a very short distance, it's already lose direction, then throughout chain will be like a fly randomly flying through all the direction. And it represents a very flexible chain. Okay? So what would it be persistence lens for other polymer we're going to talk about in this class? How about polystyrene? Polystyrene is flexible or rigid? How about, let's say, comparative polystyrene versus DNA? Much softer, right? How about versus polyethylene or more rigid? And how about PDMS?
Flexible.
So,
This is pretty flexible.
yeah, PDMS is very flexible. So if you, Sonia Campbell textbook, so one more time. I will give a little bit leak for the next class. If you look at persistence lens, it's actually already written here in the table 6.1. LP is described in terms of angstroms here. So most of the polymer are very soft. Polystyrene has a persistence lens about 7.3 angstroms. 7.3. If you compare to the bond-to-bond lens, it's less than 5 bonds. Okay? So polyethylene is 5.7. It's slightly flexible, but not terribly short, right? So PDMS is 5.3, which is a little bit smaller. But they're all on the order of from 5 to about 10 angstrom. And I have a better way to explain what is persistence lens physically. It's not mean you cannot bend a little bit. It's actually roughly about persistence length when you start to see the chain start bend 90 degrees. Okay, so your chain is going straight. For the first bond, if you count how many bonds you had the chance to see statistically, your chain is turning 90 degrees. That's a persistence lens. If you compare to the lens I talked about, polystyrene took about 5 bonds to bend to 90 degrees. The material I play with, conjugate polymer, takes about 20 nanometer, which is 20 times more rigid than polystyrene. Quite amazing. And that's actually responsible to a lot of charge transport along the backbone direction, because when you have bent the backbone a lot, you discommunicate the electronic signal, okay? And the last case I want to talk about is the DNA. It's an example where it's super rigid. 200 nanometer is very, very rigid. But as I said, it's all relative, right? Think about persistence lens versus contour lens. So for the short chain of, let's say my polymer don't accept the conjugate polymer. We said persistence lens 20 nanometer. If you have contour lens is short or low molecular weight, locally they are quite rigid. But you start to polymerize, make them longer and longer. If they have now reaches molecular weight about 100 kilodalton, you now start to reach a contour lens about 50 or 60 nanometer. Then in this lens scale, we will start to see chain bending, okay? So in the next class, I'm going to stop here. And some of you ask, I cannot fully understand the question in the homework problem one. Now you should be able to understand most of it. Sophia, you have a question?
So we can say the persistence lens can be used to measure the degree of flexibility?
Yeah, yes, you certainly can do that. And it's actually intercorrelated with characteristic ratio. Persistence lens and the characteristic ratio are effectively talking about the same thing. And we will discuss in the next class why that's the case. So if you have a rigid chain, you actually would have a large persistence lens, a large characteristic ratio, okay? So you see infinity will be bigger. And that's kind of understandable because we just talk about C infinity is some sort of expansion factor for the whole chain. If you have rigid chain, your home dimension end-to-end distance will increase. And we will spend the next class to discuss about rigidity and how can we get the persistence lens for various polymer. Okay? All right. If no more questions, let's conclude this class and we meet again next Tuesday.
You have to calculate persistence length for a question.
Please?
You have to calculate persistence length for the question.
Yeah. Can you do that?
Use the formula from the book or something.
Yeah, you can use this one. So is that question 3?
That's question 1 actually.
Okay, I'll check it and get back to you. Okay. All right. Mm-hmm.